Okay, now I want to show you what is the factors affecting the color of complex ion. Okay, so they have three factors affecting the color of complex ion. Okay, so for the first one, it's a nature of coordinating ligand surrounding the metal ion. Means that it refers to the ligands. Okay, the second one is oxidation state of central, okay, a metal ion, and the third one is the nature of central metal ion. Okay, let me take a look one by one. Okay, for the first one, okay, nature of coordinating a ligand surrounding the metal ion. Okay, for ligand, okay, information of complex ion is depend on the strength of ligand. They have two types of ligand. Okay, for the first one is a strong ligand, and we also have the weak ligand. For strong ligand, it causes the splitting of the orbital higher. Okay, the splitting of orbital become higher. Okay, so in the same time, it will produce the larger energy difference. Okay, while for the weak ligand, it causes the splitting of the orbital lower. Okay, at the same time, it causes the energy difference smaller. Okay, for the second factors is oxidation state of central metal ion. Okay, for oxidation state higher, okay, so that the splitting of the orbital will be higher and the larger energy different. Okay, and the third one is the nature of central metal ion. And we know that the transition metal have a certain colors that are typical of that metal. Every transition metal have its own wavelength to be absorbed. Okay, so this is the color that for each ion. For let's say for titanium 3 plus, it will appear purple color, and vanadium 2 plus appeared purple color. Okay, this is all the nature of the central metal ion, okay, from titanium to copper. Okay, now we will focus first on the first factor, which is nature of coordinating ligand. Okay, let me see the details. Alright. Okay, so now here is the nature of coordinating ligand. Okay, surrounding the metal ion. The most important thing is you must know the strength of the ligand. Okay, so for this ligand, okay, I already list down a few ligands here. Okay, this is the spectrochemical series. Okay, which is from left, it is a strong field ligand. Okay, from left to right is a weak field ligand. Alright, so for about this weak and strong field ligand, I already explained in our previous video. Okay, for complexes, okay, of part 3. Okay, how we want to identify the weak field ligand and strong field ligand. Alright. Okay, basically for weak field ligand. Okay, it will the donor atom must have halogen, oxygen, and sulfur. Okay, while strong field ligand, it must consist of carbon, nitrogen, and phosphorus as a donor atom. Okay, so now, okay, when the presence of this kind of ligand, okay, it will affect the wavelength that will be absorbed, okay, during the excitation of electron. Okay, for the strong ligand, okay, actually from left to right, we can see that it will have a higher energy. Alright, for strong ligand, okay, the energy difference will be increasing. Okay, at the same time, frequency also be increasing. Okay, and the wavelength being decreasing. So this we apply for the Planck equation actually. So for the Planck equation, we have energy equal to hv. Alright, E is the energy, H is a Planck constant, V is a frequency. Okay, which is H. Okay, we know that frequency is 1 over lambda. Lambda means wavelength. Okay, so we can see that this energy is inversely proportional to the wavelength. So the higher the energy difference, so the smaller the wavelength. Alright? Okay. Okay, and then for colored that will be absorbed. In this wavelength. So we can explain using the color wheel. So this is the color wheel. We can refer for this color wheel in order to determine the color absorbed and the color transmitted, which is the complementary color, which is the opposite side of color is its transmitted color. Let's say that if the electron during the electron excitation, if the energy difference is correspond to the wavelength of the visible light. If the visible light that will be absorbed is orange color. Let's say it's the orange color. So what is the color transmitted? So the complementary color is the opposite of the color wheel, which is blue color will be appeared. Right? So this is how we use the color wheel. So if the color absorbed is a red color, so what is the color appeared? Green color. Right? Here is a example of a three complex ion, with a different ligand. We take a look for the central metal ion here, since it use cobalt as a central metal ion. So let me write down the electronic configuration of cobalt. Since cobalt here is a 27. So argon. For S2 and 3D7. So since all the complex ion here is using the cobalt 3 ion. So you can calculate yourself. So cobalt 3 ion. So the electronic configuration of the ion is 3D6. Since we remove the 3 electron. So now so for the electron, it consists of the electron in a 3D orbital. So we take a look for the ligand for each complex. So for the first one, we use for hexa fluorocobaltate 3 ion is we use fluoride ion. It's a fluoro. The second complex ion is hexa aqua cobalt 3 ion. We use aqua, and the third one is we use cyanide ion. So the name is hexa cyano cobalt 3 ion. So among these three ligand, cyano, aqua, and fluoro, so we can see that for cyano is the stronger ligand, followed by water, aqua, and followed by fluoro. So we take a look the crystal field splitting electron, for each complex ion here. You can see that it has different energy difference. Now we take a look for the stronger ligand first. We take a look for the stronger ligand first. So for hexacyano cobalt 3 ion, so we fill up the electron first. 1, 2, 3, 4, 5, and 6. Alright. When the presence of a cyano ligand into the cobalt ion, so it is splitting the electron, the d orbital, into two set of orbital. So here will form the energy difference here. So if you can see that this energy difference is the largest energy difference compared to the other two complex ion, because of the stronger field ligand of cyano. right? For cyanide ion. So it will form the larger different energy. Okay, so according to the Planck's equation, okay, if the larger energy means that it will form the smaller wavelength. So that's why, okay, from this uh video we can see that the uh complex ion, okay, so it will absorb the wavelength of visible light, okay, around 310 nanometer only. Okay, so okay, we back to our crystal field splitting electron here. Okay, how to distribute the electron? Okay, since cyano is the stronger field ligand and the energy difference is the largest difference. So, okay, in filling the electron in orbital, we must fill up, okay, in a lower energy only. Okay, 1, 2, 3, 4, 5, and 6. Alright, so we must pair up in a lower energy since the energy difference is larger difference. Okay, so okay, how about the colored? Okay, when the splitting occur, which is DD transition occur, okay, what happen is, okay, when the DD transition occur here, okay, okay, so what happen is, okay, DD transition occur, so we can see that the, okay, we refer to the color wheel here, 310. So 310 is located, okay, somewhere here lah. Okay, okay, 310 nanometer. Okay, so means that for hexacyano-cobalt 3 ion, it will absorb the purple color. Okay, we absorb the purple color here, and at the same time, what is the color that will be appeared? Okay, so the complementary color that will be appeared is a yellow color. So that's why, okay, for this kind of complex, it will appear as a yellow color. So we can see, okay, this complex ion is a yellow color because the complementary color is yellow. Alright. Okay, now we take a look for the second one, which is hexa aqua of cobalt 3 ion. Okay, for this kind, okay, we use aqua. Aqua is a weak field ligand. Okay, so we fill up the electron. Okay, 1, 2, 3, 4, 5, and 6 here. Okay, and then the presence of aqua is a weak field ligand here. It will splitting, okay, splitting the d orbital, okay, into two set of orbital. So here is the, okay, energy difference, which is shorter compared to the uh, uh, third one. Okay, the third complex. Okay, so now, okay, since this is the weak field ligand, so we can fill up the electron in the orbital. Okay, 1, 2, 3, okay, 4, 5, and 6. Alright, so this is the electron. Okay, how we fill up the electron. Okay, now, okay, so, okay, we take a look, okay, during the DD transition, okay, during the DD transition, okay, during the DD transition here, okay, so what is the wavelength that will be absorbed here, okay, for, hexa aqua or cobalt 3 ion, okay, the ion will be absorbed, okay, will be absorbed, okay, 600 nanometers somewhere here. Okay, so 600 somewhere here. Okay, so we can see that it absorbs the orange color. Okay, so for hexa aqua cobalt 3 ion, it will absorb orange color. And what is the complementary color? Okay, that will appear is a blue color. Okay, so this is the appeared color, the transmitted color, which is blue. Okay, so that's why for hexa aqua cobalt 3 ion, it can be seen as a blue complex ion. Alright, okay. Okay, we take a look for the first complex, okay, which is hexafluorocobalt 3 ion. Okay, cobaltate 3 ion. Okay, so now we fill up the electron here. Okay, 6 same okay, cobalt 3. Okay, so when the presence of the ligand, with ligand, so now okay, we can split the orbital okay into two set of orbitals. So here is the energy difference, and we can see that the energy difference is a smaller difference only because fluoride is a weak field ligand. Okay, so let's we fill up the electron. Okay, so 1 2 3 4 5 and 6. All right. Okay, and then okay, let's we do the DD transition. Okay, we DD transition. Okay, so we pay up for the upper one. Okay, so now during the DD transition, we can see that the electron absorb the wavelength okay around 700 nanometer. Okay, 700 nanometer. Okay, 700 nanometer. Okay, so where is the located of 700 nanometer? Okay, here. Okay, here is the 700 nanometer. Means that during the DD transition, it will absorb the red color here. Okay, red color okay will be absorbed. Okay, so what is the complementary color of red? Okay, so this is the green color. So that's why for cobalt, okay, for hexafluorocobalt cobaltate 3 ion, it will be seen as a green complex. Okay, because the complementary color is green, it's a green color. Okay, so hope you will understand by referring to the three example here. Okay, so as a conclusion for this, we can say that okay, for the smaller energy difference, okay, it will give the different the wavelength higher. Okay, for smaller energy, okay, for smaller energy difference, it will give the longer wavelength. Okay, why the higher energy difference we give the shorter wavelength. Okay, so remember the Planck equation. Okay, for the Planck equation, which is okay E equal to HV, which is equal to H1 over lambda. So this is the Planck equation which is applied in the formation of colored compound. Okay. Okay, now let me see the second factor, which is oxidation state of central metal. Okay, and as listed here, okay, which is the higher oxidation state, it will split the higher d orbital, which is it will produce the larger energy difference. Okay, now. Okay, let me see here. Okay, now I give you the two example. Okay, for iron. Okay, which is the first one is a hexaaqua iron 2 plus. Alright, so here is the iron 2 plus. Okay, while the other one is a hexaaqua iron 3 plus. So here is the iron 3 plus. Okay, now okay, let's we compare the both of iron. Okay, so okay, we take a look for the iron 2 plus first. Okay, for iron 2 plus, okay, for iron as we do earlier, okay, what is the central metal ion electron configuration is we use iron 2 plus. So okay, its electronic configuration okay is argon 3D. Okay, 3D6. Okay, okay, it's only remove 2 outer electrons. So for degenerate orbital, okay, fill out the electron first. Okay, 3, okay, 5 and 6. Okay, so now is we have 6 electron in a 3D orbital. Okay, when the presence of equal ligand, so it will split up the orbital into two set of orbital level. Okay, so now, okay, so it will produce the energy different here. Okay, so what is the electron? We just fill up 5 and 6 here. Okay, so now this is the energy difference. Okay, energy difference of iron to plus neutral metal. Okay, so let's compare to the iron 3 plus. Okay, so from this crystal field splitting electron, okay, we can see that for iron 3 plus, okay, the energy difference is larger. Okay, you can see that the energy difference here is larger. Okay, larger difference here compared to iron 2 plus. Okay, so we fill up the electron first. Okay, 1, 2, 3, 4 and 5. Okay, since it is a iron 3 plus. Okay, this is iron 3 plus. So electronic configuration is 3D 5. So it contains of 5 electrons in a 3D orbital for the degenerate orbital. Okay, when the presence of ligand, so it is splitting the d orbital into two set. Okay, into two set of the orbital, and now we can see that it have a higher energy difference. So okay, we will fill out the electron here. Okay, so now is what we can say here, that the higher energy difference here, so it will get the shorter wavelength. Okay, why for the smaller energy difference, so the wavelength will get longer. Okay, so that's why for this case, for the different oxidation state of iron here, okay, we can see that the shorter wavelength of light is absorbed uh, for for iron 3 plus. So what is the electron? Okay, what is the wavelength absorbed by the iron 3 plus? Okay, so the iron 3 plus. Okay, so here is the iron 3 plus. Okay, which is the wavelength is shorter. Okay, compared to the iron 2 plus. So for iron 2 plus, the for iron 2 plus, it will absorb the longer wavelength. Okay, so the reading is around this area, which is red. Okay, so for iron 2 plus, okay, for iron 2 plus, it will absorb red color, while for iron 3 plus, it will absorb violet color. So what is the complementary color that will transmitted by iron 3 plus? Okay, so for iron 3 plus, okay, the color will be appeared in a green, in a yellow. Okay, in a yellow. Okay, while for iron 2 plus, okay, for iron 2 plus, okay, for the complementary color here is a green. So that's why, okay, so that's why for okay, for iron 2 plus, okay, the ion complex will appear in a green color, while for iron 3 plus it will appear yellow color. Alright, so the difference of oxidation state, okay, will produce the different energy different, okay, which is it will contribute to the different color. Okay, now, okay, I continue for the third factors, which is nature of central metal ion. Okay, for this central metal ion, okay, so here is the list of color, for the list of the color for each ion of central metal. So this is the nature, which is every central metal ion have its own wavelength in absorbing the light. Okay, let we see the example here. Okay, so for example, okay, I already list the two different central metal. Okay, two different central metal ion, which is the first one. Okay, which is the first one is a copper 2 plus. So here is the copper 2 plus, while the other one is a iron 2 plus. Okay, so this is the two different central metal ion. Okay, so the changes of the iron 2 plus to copper 2 plus here. Okay, so the changes the wavelength of light that is absorbed. Okay, for iron, so actually it will absorb red light, which is a longer wavelength. Okay, so for iron, it will absorb the red wavelength. Alright, longer wavelength. So it is the natural nature for iron, which is it will absorb longer wavelength. Okay, why for copper? Okay, copper will absorb the shorter wavelength. Okay, which is it absorb the orange light. Alright, so this is copper 2 plus and this is the iron 2 plus. Alright, so how about the color transmitted? Okay, so for iron 2 plus, the complementary color that produced from the red absorbed color, okay, so it will transmit, okay, as a blue color. Okay, sorry, it's absorb the green color. Okay, will absorb the green color here. Okay, the green color. Okay, while for copper, since it's absorb the orange light, so what happen is the complementary of the orange light is a blue color. So that's why, for copper 2 plus, it will appear as a blue color. Okay, so hexa aqua copper 2 ion will appear as a blue color. Okay, while for hexa aqua iron 2 plus, it will appear as a green color. Right, so it is the depends on the nature of the central metal ion.